It is worth looking at, well, we must look at processes of soil organic carbon sequestration, because that could give you a hint on the processes that reduce the carbon uptake or increase the losses, right? They are not necessarily the same thing, but soil erosion is one thing, but what other things you could be doing with your land use that could reduce the soil's ability to take up carbon and or emit more than they would if unperturbed. Okay. Despite microbial activities, there are several ways that organic matter and its associated carbon gets stored in soils. Looking at a few things, organic carbon can chemically react with soil minerals or other organic compounds to form strong bonds. Then it's not labile anymore, and it's not accessible to microbes to break down and consume and respire, so they can be persistent organic carbon sources in soils. Organic carbon can accumulate if it is deposited deep down in the soil. So roots can take it deep down, and there are microbial activities which tend to be very strong near the surface because there is enough water and oxygen, let's say in the top 10 to 30 centimeters, and strongly declines with depth. This is, of course, because most of the carbon and nutrients that microbes need to survive is deposited on or near the surface by plants. However, roots can penetrate to deep soil depths and inject organic matter into soils as they slough through their slough tissues. In some seasonally dry environments, like parts of the Amazon basin, roots can go down to 20 meters. So even when there is a surface drought or meteorological drought, trees can do fine because they can extract water from much deeper reservoirs which don't dry up so quickly. Water can also transport organic carbon into deep soils as it percolates down. Burrowing animals and insects are good agents of organic carbon transport and deposition into deep soils. Okay, so this whole process is very important and interesting and very inhomogeneous, so hard to map globally. Organic carbon can persist in soils if conditions are more favorable for plant growth than for microbial decomposition or physical losses. So global warming in that sense, warmer surfaces, soils not only accelerate the carbon losses but also accelerate microbial metabolic rates, growth, abundance, and respiration rates as well. So that can be a negative for plant growth. Even sometimes temperatures can get so warm that even if rain is increased, it's beyond the optimal photosynthesis temperature, so photosynthesis can be degraded or retarded. The organic rich northern peatlands discussed above are an example where soil organic carbon accumulates because microbial decomposition is inhibited by lack of oxygen in soils and cold temperatures. Basically, if you have organic carbon falling, it's cold and no oxygen is not enough oxygen is available, especially if there is a high rate of deposition of, let's say, organic matter. Then it's prevented from respiring by microbial decomposition, and that can lead to peatlands, which are basically sequestered carbon, which eventually can become coal. Organic carbon can persist in soils if the organic matter it is derived from is chemically or physically difficult for microbes to break down. This happens with materials like compost, wood, waxy tissues, or in cases where microbial community lacks enzymes to break down specific types of chemical compounds. So actually some trees obviously have defense mechanism where they want to prevent insects and worms from burrowing into them, so they actually secrete, or even to avoid competition and prevent other vegetation growing nearby, so they could own the water and the soil. So all kinds of processes can prevent degradation as well. Looking again at the carbon pools and fluxes, you can see the numbers are slightly different here. Atmospheric, so this is close to being the latest. So instead of ppm, we are looking here in terms of gigaton carbon per meter squared, stock. So there is the fluxes, photosynthesis. So there is plant respiration and microbial respiration. So that's 120 and 120. There is air-sea gas exchange and phytoplankton uptake versus respiration and decomposition. So you can have very tiny differences between the influx and outflux. So to know the exact uptake, you need a very, very accurate and very long time series to make sure you have robust conclusions. Fossil fuel, cement, land use change, net terrestrial uptake, stock in soil carbon, fossil fuel pool that we talked about, surface ocean pool, deep ocean pool, reactive sediments, and the fluxes shown here. So the atmospheric carbon is CO2 concentration is increasing by 4 gigaton carbon per year. So that's not good news, right? So in terms of global homogeneity, the heterogeneity that I mentioned several times, there are now some tools like these spectral radiance measuring satellites. This is from the so-called CVIVs, Sea Viewing Wide Field of View sensor, which flew from about 1997 to 2010 or so, and then there have been several others like MODIS and others that measure chlorophyll, which has a radiant signature, and this is showing the seasonal cycle. So if you know the ocean, you probably know the open ocean production, coastal production, spring blooms in high latitudes, river plumes here, for example, Congo, Zaire, Amazon, I think this is Orinoco, and so on and so forth. But you can see the CO2 cycle we saw in the Keeling curve as well. As the sun moves north and south, the photosynthesis also picks up and dies down. So even in the deep tropics, you have strong seasonal cycle in photosynthesis, which shows up as the sawtooth pattern in the atmospheric CO2 measurement. Atmospheric CO2 is well mixed, inert gas, long residence time. So you measure it in Mauna Loa, it's going to give you a good sense of northern hemispheric concentrations, and you can measure it somewhere in the southern hemisphere to get a good sense of the southern hemisphere concentration. There is some hemispheric gradient maintained because of the rotation effects and the hard to mix aspects of carbon dioxide. Okay, so there goes my doorbell, so I'm going to stop this here and we'll come back a little bit later.